everyone. Oh, right, there is no feedback. So I would like to give you a bit of an explanation about practical property testing. I've noticed that there is a lot talked about, researched about, and written about in blog posts about property testing. And I've noticed that all of those are, well, they're often not very practical in the sense that they give you toy examples and they show you what the purpose is of the concept of property testing, but they don't really talk about what it's like to use this concept in practice. So that's what I'm going to try to talk about. So I want to talk from scratch about what property testing is, why you would use it, how it works internally, so that you have a nice mental model of what you should be thinking about when using this. And then I'm going to show you a concept called property combinators or test suite combinators, which will become apparent in a moment. And then I want to talk practically about how to property test something real world, like a web service with a database, for example. And I'm going to give you some links to relevant projects at the end, so you can have a look at all of the things I'm talking about afterwards. There should be a Q&A kind of thing here in Zoom, so that if you have any questions, please ask me immediately. Then I can reflect on what I said and maybe explain it a bit better. And hopefully we'll be able to clear it up so that everyone can follow along. There is no code to be written along with me right here, but all of the code examples that I have are, you can try them out yourself. So I'm going to get started here. Oh, one more thing. If you have a question, you're likely not the only one with that question, so make sure to be the brave person and ask the question. Okay, so let's talk about this. What is a property test? So to understand this, we have to first talk about what unit tests are. And I contrast those, but you could give it another name. It's really, it's not about the naming, it's about the concept. So a unit test can be defined as a piece of code. And if you run the piece of code, you will check, does it crash? If it crashes, then we say it fails. If it didn't crash, then it passes the test. Now, this is a definition, and you can just view the concept of an assertion as an easy way to make a program crash in this context. So here's an example of a unit test, which checks that if you have this specific list 173 and you reverse it twice, you should have the original list again. And this is a test for the reverse function, ideally. So imagine writing your own reverse function. This is a test that you could be writing. And you might be used to this kind of test for your production code, because usually you do something like this, where you have some dummy values that really don't matter for the test, but what you should be testing is what happens to those values specifically. Now, the property test equivalent of this test would look something like this. And the property test is nothing different than a unit test, except it takes an argument. And the idea is that your test should pass for any argument that you could pass in here. So in the previous example, it's actually the case that it doesn't matter which list you have. If you reverse them twice, you should get the original one again. So here's the property test that corresponds to that statement. So I'm saying here there's an argument called ls, which happens to be the list. And if I reverse this list twice, I should get the original list. I'm going to talk about how to run this in practice in a moment, but this should be it should be clear that this is what a property test is. And now we can talk about why you might want to do such a thing. And the answers are something like, you get cheaper examples because you only have to, you don't even have to think about what kind of input you want. You just have to declare for any input that you may throw at this, this is the way it should work. Because of the way the inputs are thrown at the test, in practice, that's usually using randomness or in rare cases, exhaustion. You also come up with inputs that you might not have thought of when running the test. See, the problem with testing is that you already have to know what it is that your code is supposed to be doing in order to check whether that's what it does. And property testing solves a bit of that problem by throwing random input at your code instead of just predictable self-written test examples. And then there are some negatives to property testing as well, of course. The first is that you have to still come up with the properties yourself. And this may be more difficult for most people. In fact, it definitely was for me, because now you have to think about the more general thing that your program is trying to achieve instead of just what happens for a specific input example. And then the next con is that you have to start thinking about how to get the input that you want to be throwing at the property testing. And you have to understand what shrinking does and how that works. And in practice, in practice, there are some rough edges to it that you really need to understand before you can start doing something like this. So I'm going to go on with showing you what this kind of test looks like when you try to run it. So here is an example of using a popular Haskell library called QuickCheck to run a property test. Here I'm saying, QuickCheck, run this property test, and it says, OK, it passed 100 tests. There are other libraries that you can do this with, but they all basically do the same thing, where there's a unit test with an argument, which we have now called a property test, and then it somehow provides input to that. So there's QuickCheck, which uses randomness, then there's SmallCheck, which uses exhaustiveness, etc., etc. Point is, it's the concept of a property test that you should be worrying about, and not yet the framework. Then I'm going to show you a little bit about the internal workings of such a generator. Now, I've used the QuickCheck model of a generator in order to show the concept. However, you can find a similar concept in all of the libraries that you'll be working with. So to think about a generator, in Haskell, we use a type parameter to show you a generator of what you're generating. So in this case, we have a generator for A's. And the idea is that this will produce random A's for us to pass into the tests. And now, it's really important that you realize that this is for the purpose of testing and not another reason why you would use randomness. So sometimes we do it a bit differently from the way randomness works in other cases. So you should never use, for example, a generator in property testing for cryptographic randomness, because you'll just end up doing the wrong things. So the way this works is a seed gets put in, and the seed is used to determine the randomness from the start. So it's actually not random at all. It's pseudo-random, and it's determined entirely by the seed you choose up front. And you should be choosing a seed up front that is fixed, so that whenever you run your test suite, it's reproducible and not flaky because of this randomness. And then the second thing that you need to pass in may be a bit confusing. It's called the size parameter. Now, the size parameter is used to guide the generation of things that you can't really choose a uniform value from. For example, if you want to choose a random integer, you might think, well, there are 2 to the 32 integers in the specific type I'm using, so I can just use any one of them and it'll work. Then there are other types, like, for example, a list of integers, where it may not be so obvious which kind of list you want to generate, because there is no obvious choice between saying I want a list of 2 elements or maybe generate a random list of 200,000 elements. It's not really obvious which one you should be choosing. And that's where the size parameter comes in. So this size parameter allows you to determine how complex the value that you want to be generating should be, and maybe also something about the memory footprint, but there are really no clear semantics about what this should be doing. It's just that if the size parameter gets bigger, the list should be bigger, and maybe the values in the list should be bigger, so that will allow you to guide the generation of it. OK. That should be the internal workings and the concept of a properties test. If there are any questions until here, please put them in the chat, and I can answer them immediately, because now we're going to go to a bit more complex concepts. OK, looks like no questions. That's good. Well, good in the sense that it may mean that I've explained things well. All right, on to the next thing. The other thing you need to know about is shrinking. So what happens if one of these tests fails? If a unit test fails, you just get, it failed. And then you know nothing else, because you can just look at the code to see what was supposed to happen. If a property test fails, you get a counterexample. And here is a nice property with a nice counterexample. So the property here is that I was trying to test, which it turns out it doesn't hold, and we're going to see that in a moment, is that if you uppercase all the characters in a string, then all of the characters in the string become uppercase. And QuickCheck ran this test and said, this is wrong, and here is a counterexample. Now, it definitely isn't obvious to me why this is a counterexample for such a property. In fact, as far as I can tell, this property should still hold. And what shrinking does is it makes this counterexample smaller so that it may be easier to reason about as a human to debug the problem. And in fact, the counterexample that I'm showing here is explicitly with turning shrinking off. Now, if I turn shrinking back on, you get an output something like this. It says here, it's still false, And after 3 tests, I did 1 shrink, and I came up with this other counterexample that is smaller. And here is a counterexample. It's a string with 1 character of the character 1. And the reason why the property fails here is because if you uppercase 1, it stays the same, and 1 turns out not to be uppercased according to is upper. And the way shrinking works behind the scenes is that it tries to turn a counterexample of type A, which is whichever you're looking at, into a list of A's that are smaller to consider. And the way that works is whenever a counterexample is found, it is shrunk. So this list is produced. And then from front to back, QuickCheck goes over it and says, this smaller version of the counterexample, does it still fail the test? If it still fails the test, that means it's probably easier to reason about. And then we can just show that to the user instead of the original one that makes no sense for debugging. So that's how shrinking works in practice. Going on, there are some ways to generate values using custom generators. And there are some building blocks to do this. And here are the building blocks that I'm going to be talking about. There's arbitrary, which allows you to generate arbitrary values of this given type class that QuickCheck has implemented. So most of the values that you might be working with are probably already in here. So like integers, strings, doubles, whatever. And then there are 2 more important building blocks. One is called such_that, which says here is a generator and here is a predicate. If whatever you generated matches the predicate, then let it through. Otherwise, try again. And this builds a new generator. And then the other one you should know about is called elements, which is just for a given list, generate any one of those elements. And by putting these together, you can get new generators of whatever you'd like. And of course, this being Haskell, gen is a functor, an applicative, and a monad, and you can use that for all the good reasons that you might want to. And here's an example. So here I have 2 generators for characters. One is for a suit of a card, and these are playing cards. So I managed to use the fact that Haskell accepts Unicode characters in source code, somehow in a talk. And the second one is generate the values of these cards. And I actually forgot the 10 here, I just noticed. Anyway, so any one of these values would be generated. And now because this, this generator is both a functor and an applicative, I can do this and get 2 cards, get a card with a suit and a value, for example. Or I can even get a list of cards by just running that multiple times. Now, forget this implementation. I just wanted to show you that it's a monad, and that you can just use that in the ways you want. This is actually the wrong way to do things, but it's a nice way of showing this. And then in order to use a size parameter, there are 2 functions two other functions you should know about. One is called sized, which allows you to use the parameter somehow. So you get the size parameter and you turn it into a generator, and then you have a generator. Or you can set the size for another generator that you pass in, and that makes a new generator as well. So here's an example of a generator that might generate 15 integers in a very convoluted way. I'm saying here, set the size parameter to 15. And then we're going to use this one, call it n. So the n will be 15 here. And then we're just going to replicate 15 arbitrary integers. So that's a way to write your own generators. And you would use these when your property doesn't hold for an arbitrary value, or maybe because you have a special kind of input value, in order to still write a property without having to use the default one, which would make the property fail. And to use one of these custom generators, you would use something like this. I have a custom generator here called myCustomGenerator that generates V's. And then there's a function in the, I think it's in QuickCheck, yes, that says give for any generator here and a property that I can use the generator for, turn it into a property. And so I can say for all my custom generator, run this property of any V, and that will run the property for you with that specific custom generator. And if you want to add shrinking to that as well, you can have your custom shrinking function as well. And there is a function called for all shrink in QuickCheck, which allows you to specify a special shrinking function, or even the default one. OK, is everything clear up till here? Because now I'm going to talk about the dangers of using property testing and what you should be aware of. No questions so far, it seems. All good. Oh, nice. I can see the chat. Super. So there are some dangers with respect to, I just read someone saying we're here for the tricky bits. Okay, the tricky bits are coming now. So here's one of the issues with shrinking. If you have a generator that is custom, then you have to make sure that the invariants that you want to maintain with your generator are also maintained by your shrinking function. And I'm going to show you an example where this goes wrong right here. Suppose I am a bit of a naive programmer, and I think that all numbers larger than 5 are even. And you must be a special kind of naive to come up with such a test, but it's really good, an example here. So what I would write is something like, for all arbitrary integers that are larger than 5, test that if the number is larger than 5, it's also even. And here I'm making the explicit mistake of using the default shrinking function that does not maintain the invariant of the integers being larger than 5. Then I might run this and get the output false. Not all numbers larger than 5 are even. In fact, there is a beautiful counterexample, 0. And then you might be confused and think, why is 0 a counterexample of numbers larger than 5 being even? And here's the way that would happen. You might generate a value, for example, 7, which is larger than 5 and not even. So it's a good counterexample. And it passes this custom generator. And the test would fail. And then QuickCheck would think, oh, but this is probably too complex of a counterexample, so we're going to try to shrink it. And then it uses the default shrinking function, which shrinks to the most easy to reason about integer for you. And then it will give you a 0, and it runs 0 through the test. And it says, well, 0 is not larger than 5, so it fails. OK, here's a nice counterexample for your property. And the real problem here is that 0 is a counterexample that failed for a different reason then 7 failed. So there is an issue there, and you have to make sure that the shrinking function maintains your invariant of the generator. And the way you do that is, for example, by writing filter greater than 5 shrink instead of, or dot shrink instead of just shrink. And then you get a nice counterexample of 7. OK, so that's lesson 1, maintain the invariance of your generator. The next issue is not so much about debugging, but more about performance. So here it is. So there is this function I told you about, such that, which can filter a predicate for your generator. And I'm going to show you 2 different generators that generate the exact same values. And one of them is going to take ages to generate anything, and the other one is going to return immediately. This first generator says pure 100, and it just immediately returns 100 without using any randomness. And the second generator will generate a random integer and then filter it only the ones that are equal to 100. And obviously, the second one is going to take a lot longer to produce anything. So we have to watch out for 2 possibilities when using such that. One is either you use predicates that are rarely satisfied, like, for example, equal to 100, or you use really expensive predicates. For example, this number is a busy beaver number, or a prime, or, oops, wrong button. OK, anyway. So far, so good. So watch out for slow generators. And I've noticed in practice, whenever you have a slow test suite with property tests, it's probably because your generators are slow and not because your tests are slow. Because the standard way of running a property test is running it 100 times. Next danger is the size parameter. So the size parameter allows us to generate values in increasing size, increasing complexity. However, there may be reasons why a property test passes just because of the size parameter. So watch out with property tests that depend on the size parameter for its passing. For example, this one says every list is shorter than 100 elements. And QuickCheck says, yep, that passed the test. And the way you should read this is not, oh, every list is smaller than 100 elements, but rather QuickCheck generate 100 lists, and they were all smaller than 100 elements. And then you can start thinking about why it did that. And in fact, if you arbitrarily increase the size from maximum 30 to exactly 200, like I did here, then it will give you a nice counterexample. So the issue to watch out for here is watch out for properties that depend on the size parameter. Then there's another problem with the size parameter, which is that if you do the stupid thing for recursive structures, you might end up with an exponential generator. So here is a nice data type, which is a tree without any values. And I just did that to make everything fit on the slide. I'm saying here a tree is either a leaf or a branch with two trees. And the standard implementation is something like either you generate a leaf or you generate a branch with two more trees underneath. And if I now have a size function for the size of the leaf, and this will just tell me how many leaves there are in the tree. Then if I look at the distribution of the outputs of running this generator for size 1 tree, then you will get sizes like 1, 80,000, 100, 1,312, etc. And the problem here is that the size parameter was not used in a linear way. And that becomes a problem when you have enormous inputs, and then your test suite will start eating up all your memory. So the way you should do this is by writing a custom generator that uses the size parameter in a new way. For example, here we say that if the size is exactly 1 or 0, but the size parameter shouldn't be 0, then just return a leaf. If it's anything else, then split it into two pieces. There is this function called genSplit, which splits n into two numbers that add up to n. And then resize the left side of the tree to A and resize the right side of the tree to B, and then generate accordingly. And this gives you nice linear sized trees. But this size of the tree, note that you have to think about the fact that now your tree is linearly sized in the number of leaves and not in the depth, for example. So it's something you should take care of when writing these kind of things. Okay, so those are the dangers. The next things I'm going to talk about are when you use this in practice, how do you make your life easier? And then the last thing I'll be talking about is how do you use this in practice for a real project that uses databases, for example. Any questions until here? These were the tricky bits. So feel free to bombard me with questions now. All right. Should the tree sizing use genSplit n-1? No, it shouldn't, because if this size is 0, then the size becomes negative, and then you get errors from QuickCheck. It's a good question, because you might want to consider the constructor also to have size 1, for example. But in practice, you run into trouble where the size parameters must not be negative. So actually, I should have written 0 here instead of 1, but it doesn't matter for our presentation, I think. Okay, going on. So the next thing I want to talk about are property combinators. So it turns out that you reuse similar properties a lot. And some of them are mathematical, and those are the ones I'm going to give you as an example. I know that Haskellers usually like these kind of mathematical examples. This is not the kind of thing you would usually use a lot, but it's a good way to make my point here. So what I'm saying here is that greater than or equal to is reflexive, which means that every value is greater than or equal to itself. And I might say this, for any a greater than or equal to a should be true. And actually the same holds for lesser than or equal to. And what I'm trying to do with a combinator is factor out this concept. And here is a property combinator, as we call it, which is where I say for any value and any binary predicate, there was a word for this, for any relation, binary relation, I can test whether it's reflexive. And so I just pass in the function, the binary relation, and I do that, and the test happens within here. So this is a property combinator. And then it looks like this. And you just say, well, reflexivity holds for that. And then there are others, of course, and you can make as many of these as you want. And we've already done that. So you can go and look at the library that I'm going to show you later. But you can go even further. You can go to the point where you generate an entire test suite instead of in only one property. And here is an example. This is called the equality specification, which is where I say the equality for this type A makes sense. And you can have a property test suite combinator where you pass in a function or anything else. In this case, we're passing in only a type. And we're doing this with a trick with two language extensions. The first one is called scope type variables, which allows me to specify a type explicitly in the type annotation. And the second one is called allow ambiguous types, which allows me to specify this type and then not use it anywhere. And the the way I use this scope type variables now allows me to use this value A somewhere in the implementation, and then the compiler will know what I'm talking about. And at the use site, it looks something like this. You need type applications. By the way, you could just as well have done this with a proxy of A and it'll work, but this is just nicer as an API. I'm saying, give me the equality specification for int, and I might get output like this, where I say equals equals, the equality function is reflexive, transitive, symmetric, and it's equivalent to not equals, and not equals is anti-reflexive and equivalent to not equals. And I get all of these, so this is 6 tests times 100 cases, so 600 cases tested for a single line of code. And you can do this for all sorts of things. But another nice example that I should probably have used instead is I have database types for things that are in my database tables in my database, and they correspond to types. And there are some things that I always want to have hold for my database types. One is they have a generator. Second is when you put them in a database and you get them back out again, you get the same thing. I want them all to be hashable for some reason, et cetera, et cetera. And then you can make a test suite combinator that makes sure to test all of these things for you, and just have a test suite combinator invocation in your test suite for all of your database types. Okay, now on to the practical usages of property testing. I have an example here. What did I do? I have an example here of an architecture where we have some tests that will call a web server, and the web server will call some sort of database. And the way we want to do this is we will set up everything that's necessary around every test so that no state is shared. You could share the state to save some complexity or some time. In this case, we won't do that, but it's definitely possible. You then run everything and then tear everything down again after each test. And you'll need a function that looks a bit like this. It's called WithMyApp. And what it will do is it'll take a given function that will use some sort of value that you can use to contact your service. I call it a client environment, and run a test. And by supplying this test that can use the client environment, I have to now turn that into some IO action. And the way that happens in practice is you set up your application, you set up your databases, you do that maybe with a with function or however you want. And then you produce this client environment, in this case, by saying, well, the service will be available on the local host on the given port. And then you pass that into the test. Now, specifically for Y applications, Warp has a special function called test with application, which will spin up your application in the background, give you a nice port so that you don't have to specify which one yourself, and then you can use that however you wish. And it'll deal with exceptions in the right way for you so that testing works quite nicely. And once we've got such a thing, we will write what's called a spec with function. And spec with is something that denotes a test suite where every test might have access to this client end. And then using WithMyApp, we can turn a test suite that can use the client end into a test suite that doesn't. And here is an example of what that would look like in practice. This WithMyServer turns a test suite that uses the client environment into a test suite that doesn't. And then I might want to write a test like this. I'm going to give you some details in a moment, where here are some types to keep in mind. If I want to call my API, I do it in a client monad that uses the client environment, and I run it using client environment, using run client, which takes the client environment, takes a client monad action and turns it into an IO action. Now, to break this down into pieces, here's what you would want to write. And what I'm writing here is a function that says, if I call my API twice, I should get the same result twice. Now, there are some tricky bits that you might need, but what I'm saying here is, for any argument that I'm going to figure out later, call my API, get a result, do the same thing a second time, and then make sure that those two are equal after contacting the client with this client environment. The argument we're going to get from randomness by saying property argument do, And the client environment we're going to get from the test framework by saying when I'm calling the API, it gets the same result twice for any argument that I might use. And now I have a test suite that uses this client environment. And then I say with my app, turn it back into a test suite that doesn't know anything about the fact that I'm going to call my service. And then I have my test suite that I can just run, and it'll set everything up for me and tear everything down again for me and figure out how to run everything so that the exceptions match up, so that I can just run my test suite and not have to think about it anymore. And this turns the whole concept into a composable, nicely encapsulated thing that you can just run. Okay, so that's practically how do you run property tests with a database or a service or whatever. You just use this kind of setup. If you know how to set up your database, run a test in between, and then tear it down again, then you can do that once, and from there on only worry about the test itself. Any questions until here? Otherwise, I'm going to start listing some relevant projects that you can go look at. Okay, so here are the projects that you will definitely want to have a look at. There's QuickCheck, which is the original property testing in Haskell project. There is definitely something similar for Scala, but I'm not a Scala developer, so I couldn't tell you, to be honest. It's probably even just called QuickCheck. I'm not sure. And then the second thing you want to look at is called HSpec, which is, I think now it's the standard way of doing things. It's a test framework that requires you to specify what it is that your test suite is supposed to be doing, and it hooks in nicely with QuickCheck. So you can just write a property, and HSpec will just say, oh, that's something I can run, let's run it. And then there's Validity, which is a new take on the way generators should work. And it also comes with a whole bunch of pre-prepared, actually, it should just be prepared, I guess. What does paired mean? Anyway, so it comes with property combinators in the library, and it comes with test suite combinators in the library as well. And it does the whole generation thing a little bit differently to take sizes into account better and to generate more nasty inputs so that you are definitely sure that your property holds for every value.